Welcome back. I think that we are well done with going through some of the simple machines. I think we have a decent understanding of a good number of them, just the basics behind them. You will obviously delve into them deeper when you take physics in college, as I'm sure you all will. But I think it's worth our while to talk about a term that we didn't learn at all last year, a term that gets thrown around a lot in the world. I'm sure you've all heard of momentum. But momentum has a very, very specific physics definition. And momentum is a very interesting quantity that we're going to kind of explain right now. Simple picture of a bowling ball using its momentum to knock down the pins. Obviously, things that have a lot of momentum, they say that you can't stop them. The analogy is used in sports. As a team, is building momentum, it's doing well, it's tough to stop. And such. Okay, what is momentum? Momentum is very simply defined as inertia in motion. So we know that inertia is the tendency to resist a change in motion, right? So if we say it's inertia in motion, we're saying an object that's already moving, an object that is already moving, and so it wants to keep moving. It doesn't want to slow down. It just wants to maintain its motion. So that kind of makes sense with the definition that we were talking about before. Mathematically, momentum equals mass times velocity. This is important. Momentum equals mass times velocity. Remember, force equals mass times acceleration. So momentum equals mass times velocity. It's very, very similar. So, we had a FEMA triangle. Oh, and of course, the symbol for momentum in equations is obviously going to be P, clearly, because what other letter would you think of to abbreviate momentum than P? P equals mass times velocity, mv. So real simple, like multiplying, dividing simple. Obviously, it's going to get a little more complicated, but units for momentum. Well, let's think about it. So what's the unit for mass? The unit for mass is kg. The unit for velocity is meters per second. So one way of doing this is kilogram per meter second, okay? Now, for those of you who know calculus, this unit might make a little bit more sense. Because if you think about it, momentum and force could be a derivative of each other. I'm not going to explain that. If you are calculus of each other, I will go ahead and let you consider that. But essentially, if force, you know what? No, it's not worth it. Just accept. Just accept that these are the two units that you have for momentum. Newton seconds or kilogram meters per second. Okay? That's it. Simple. So, obviously, yes, if an object is not moving, it has no momentum. If the velocity is 0, the p would then be 0. The mass could never really be 0, because if the mass is 0, then you're not talking about anything. And all objects would have a mass. So the mass is never going to be 0. All right, real simple, like painfully simple. What is the momentum of a 2 kilogram basketball thrown 8 meters per second? Mass times velocity. It's so easy. 6 kilograms per meter per second. So if you forget the units, you can literally just combine them. Okay, so what is the mass of a car that while traveling 4 meters per second has a momentum of 16,000 Newton seconds? Okay, Newton seconds, so that's just the momentum. It's another unit, but it's fine. Momentum divided by velocity is going to be the mass. So the mass would, of course, be 4,000 kg. Mass is kg. This is really simple. How fast? So we're looking for velocity. 6 kilogram bird flying with 40. Just divide. Divide. It's that easy. 40 over 6. I'm going to keep it moving. And that says, what is the momentum of a 10,000 kilogram truck at rest? 0. you don't have momentum. Oh, I didn't actually. You don't actually have momentum when you're at rest. Okay? Simple. So, all right, this is where it gets a little tricky though. So momentum can change, obviously, because velocity can change. So in order to change the velocity, you have to have an acceleration. In order to have an acceleration, you need to have a force. That's Newton's second law. So adding a force to an object provides an acceleration, which changes the velocity and the momentum. So let's just think about how this is connected. So force creates an acceleration, which changes velocity and therefore changes momentum. And the longer that a force is applied, the greater the change in the momentum will be. So let's think about it. If you push something a little bit, you don't accelerate it that much. Therefore, you don't change its velocity that much. Therefore, you don't change its momentum that much. The key here is not necessarily what the actual momentums are, but we're talking now about changing momentum. So let's take a look at this. Impulse. Impulse is a force that acts on an object over a period of time. Or another way of thinking about impulse is the change in momentum. So impulse can be you can think of it like this. Impulse is force over a period of time. So delta t, remember delta means change in, or period in time, change in time. So the reason why it's delta is if we were to graph momentum, which we will not graph momentum this year. I wanted to, but it's just not going to happen. But if we were to graph momentum, the delta t would become really important, because if you remember graphing earlier in the year, it wasn't just t. Like if you had an axis 0, 1, 2, 3, 4, we didn't care about that. We cared about like the delta t. That would have been the delta t. But that's what we're talking about here when we say delta t. Okay, so impulse is just force times the amount of time that force is being applied. That's all. Well, that makes sense. So impulse is also known as the change in momentum. So this is kind of important. Impulse is the change in momentum. So force over a period of time equals, and the delta means change, and momentum is mv. Another way of writing this equation is force times the time interval equals the delta p, because p is mv. So all I'm saying here is that if you have a big impulse, you have a big change in momentum. They are the same thing. Every time we use the word impulse, we mean change in momentum. Delta means change, and this is momentum. So in this instance, force and time are inversely proportional. When we're talking about impulse, if we're changing a momentum, so let's just say, well, we're going to get into a few examples, but let's just say like you drop a pen onto the ground and it hits the floor. It stops quickly. So its change in momentum, its impulse, is high. Let's just say you drop a pen into a pillow. Well, does the pen stop moving as soon as it hits the pillow? Maybe, but maybe it takes some time to kind of press the pillow down a little bit. Maybe you can see this more if you get a heavier object, like a book. And the process of pressing it down means that you're adding more time to which the force is being applied. So what's happening is, if you have more time, the object has to change its momentum, the less force is required. And the less time an object has to change its momentum, the more force is required. So let's think about this in a practical sense. So what does this mean? Here's a cartoon that I found that kind of illustrates this pretty well. It's a boxer, and he's getting hit in the face. So the momentum of the other guy's hit is being transferred to his face. He's going to stop the punch. But the question is, does he want to lead into the punch, or does he want to lean away from the punch or move with the punch? If he leans into the punch, what he's doing is he's causing the punch to stop quickly. That's what's happening here. Because the punch stops quickly, it stops in a small time, which means he experiences a much larger force. However, if he moves with the punch hits his face and kind of moves with it, what happens is he's increasing the time that the punch has to stop. And as the time goes up, the force he experiences also decreases because they are inversely proportional. Because the change of momentum is the same. The change of momentum is causing the hit to go from whatever speed it was to 0. That the only variables that they can affect are how much force you feel and the time it takes. So remember, the impulse is a change in momentum. And if an object falls and bounces, it actually requires more impulse than simply stopping because it's changing its direction. If you actually think about velocities, the change in velocity, going from 3 to 0 is actually going to be less than going from 3 to -1, changing direction. So you may notice, and the reason why I have the picture of the guy breaking the wood, you may notice that in competitions like that, where they're trying to go ahead and use their hand to break it, what they want to do is they want to have their hand make contact with the wood or the brick in a super short period of time, and they actually want the material to slightly bounce their hand. Because, well, one, if their hand is in contact with the material for a short period of time, they exert actually more force on it and can break it more easily. And two, if they can cause the object to help bounce the hand back up, you're applying even more force, you're getting more of a push on the object, you can cause it to break. So a lot of martial artists really take advantage of these concepts of physics to go ahead and do these incredible feats. Okay, so here is a kind of a theoretical question. If you are falling, let's just say you were falling off a building, and you had to land in water, you had a trampoline, and then you had this giant air pillow here. Which would you rather land on? Well, if any of you have ever fallen a great distance into water, you will know that water is not fun to land in. But that's not because it's bad for momentum, that's because of something called surface tension. And I think I even mentioned this before. If you're falling a great distance and you have like stones in your pocket, if you throw the stones at the water, or the water is choppy and wavy, it won't have as much surface tension, and getting into the water will not be as painful. If you fall like 50, 70 feet into water, it can be very, very painful because of the surface tension. But if it's choppy water, if it's wavy, if it's not flat, if something is already breaking the surface tension, what happens is you go into the water, and what the water does is the water takes a lot of time to slow you down. With more time, you experience less force. And if anyone is really falling into water going fast, you go fairly deep. And that's okay because it's slowing you down over a longer period of time. A trampoline would be pretty good, but the problem with a trampoline is that it could only go this little distance before it hits the ground. So let's just say it's slowing you down, but once it hits the ground, it can't bend anymore. And then you just hit the ground. So a trampoline is actually a terrible thing to have to jump off a building. And I'm sure you've seen YouTube fails of people thinking you could take a trampoline like this and jump off a 3-story building. They hit the trampoline, but they have so much momentum that the trampoline cannot stop them, and they still hit the ground. An air pillow like this is a giant pillow, and look, it's like the size of a story. I would most want to draw on the air pillow because the surface tension of the water would be painful. Because if I fell on this, it is a giant pillow, and it has plenty of space for me to fall down and to give me more time to stop. So essentially, when you think of momentum, you want to think about which of the things is going to give you the most time to stop. Because the change of the momentum is the same in either case. You're going very fast to 0 in all 3 cases. But the only difference is how fast you do that. Oh, if you just hit concrete, you would go from very fast to 0 very quickly because the concrete would not move. So the time it would take would be very small, and therefore the force would be very big. It is a practical example of impulse. Okay. As promised, we are moving away from the worksheets that you kind of just do your problems out and send them to me. Today is going to be a physics classroom. The physics classroom is going to be about impulse. So here's what's happening. I'm going to go through 2 of the sample problems for you. I'm not doing them all. There's one type of problem that I'm not going to explain. I trust you'll be able to figure out. But what it says here, it says initial state. And it says velocity is 4 and the mass is 4. And I know that P equals mv. Okay, 4 times 4 is 16. Positive. I don't need to stress that. Newton seconds. Let's use Newton seconds. Okay, and it ends up with a momentum of 7 times 4 mass. Okay, so let's just go ahead and say 28. All it wants to know is you just have to pick one of the 5 things down here that would change the momentum from 16 to 28. How much is the momentum changing from 16 to 28? It is increasing 12 Newton seconds to the right. So which of these shows 12 Newton seconds to the right? Well, no. This is 11 Newton seconds to the right. 28 minus 16 is 12, by the way. Oh, as force and time. Oh, to turn force and time into a Newton seconds, you've got to multiply them. Remember, the change in momentum is the force times the change in time. So, in this case, 3 times 3 is 9. 9 is not 12. It's not that one. The change in momentum, it's not 12. It can't be that one. It's got to be this one. And it can't be this one because this is actually a change of 48. So what you have to do is you have to find the momentum that's going to go here that is going to be combined to this to make it equal this. 16 plus 12 equals 28. That's it. You will need both the F delta T and P equals mv equations. So then of course it's going to get a little bit harder because then it says what 2 things do you need? But the process is still the same. So we're starting with a momentum here of 12 Newton seconds to the right. Pay attention to direction. They will get you with direction. Trust me on that one. And it ends up with 28 to the right. Again, that math is so easy. I don't really want to go over that. But what's the change? What is the change? So the change is we have to find 2 things down here that in total equal 16 Newton seconds. So this is what I would recommend you do. I recommend you solve them out for momentum. So, okay, to get momentum, it's force times time. So this is actually plus 16. All right? You know what? Forget the units for right now. This is just plus 24. That it already is giving you the momentum. This is, again, impulse is a change in momentum. And that's exactly what we're solving for. Why did I write their unit? This one is multiply this plus 16. And here's the impulse of plus 8. It's just said. So what you have to do is you actually have to click 2 of these things. What 2 things here? So your gut instinct is like, oh, it's 16, 16. Those are the answers. But what we're saying is if you had 16 here and 16 here, if you had 16 in both of them, it would actually give you a total change of 32. So what you have to do is you have to find 2 things that add up to positive 16. What 2 things here are going to add up to positive 16? These are the 2 you would select because those are the 2 that would add up to the difference between your starting and your ending. That's the key. Positive 24 plus negative 8 is positive 16, which is what we were trying to get, the difference between where we started and ended. So, I know I'll see questions about this, but just take your time and think about it. You can do this. And you know the deal. I've got office hours daily. Please come see me, except for this Friday. I actually get to go to BL and clean out my room because they're going to let teachers in, one teacher per day. And Friday's my day, so I won't be here for office hours. And yeah, I'm here. So good luck, and I will see you guys next time.